Hey guys, what's up? Eddie Aho here with KissAnalog.com. Hey, today's an exciting day. We're wrapping something up. Yeah, I have that big old power supply still on the bench. I know, you're getting tired of seeing it. I hope you like this video. We're going to wrap things up and I'm going to kind of combine a bunch of stuff together real quick, okay? Now, what we're showing, there's a number of things I want to show. I want you to get real familiar with what waveforms look like and one of these low frequency power supplies, okay? And then we're going to go on to our high frequency power supply and you'll see the differences. It'll be more obvious to you. And one of the things I keep on jabbing is the audiophile guys, the nuts who think that the power cable makes a difference. So the power from the wall, relatively clean, you know. Now I'm taking it from this AC power source, so it is really clean. So I'm getting the best case. And I'm going to show you how we muck it up. I mean, we just put it in a wash machine and you know, beat the crap out of it. So it comes off as a 120 volts. Now, by the way, because of my load and the turns ratio on the transformer, I can only take this up to 90 volts. But we're going to go more power this time. I'm going to go up to, I don't know, over 100 watts. I can go to 300. I think I'll go about 150 watts, somewhere around there. We'll see. Okay? Just, you know, showing a point. Okay? So we're going to take nice clean voltage off this thing. And then we're going to go to a transformer and it drops voltage down. That's what they do. But then it goes to the bridge rectifier. Now, one point I want to make is I'm going to show you the power factor too. You know, in school they show you sine waves. They say, well, see, the sine waves are off, the power factors, the angle of the difference, and blah, 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 and all this kind of stuff. What they never, I don't think they ever tell you in school. And, you know, there are some power courses now and advanced classes that maybe they get into this. But on the job, I've had to teach guys, some of the teams I've worked with, on how you do proper power factor, especially when you go to three-phase. But even on single-phase, that current is no longer sinusoidal, okay? So you don't do power factor with two sine waves with some phase difference between them. That's part of it. There's a phase shift. But it's only with the harmonic, the main harmonic, fundamental frequency. The other part of the power factor is all the lost power and all the high frequency harmonics, okay? So that's garbage stuff. So in these kind of power supplies, power factor is not good. That's not a good thing. That's why today we have power factor correction, active power factor correction. We've had a passive power factor correction in some plants that don't want to pay all that extra money to bring in the apparent power to use the real power, you know, all that stuff. Anyway, just want to throw that out there. Let's move on. So it comes in here, but because the rectifiers are pulsing, they're turning it on and off, you get these pulsating currents. So it takes that relatively nice looking clean 60 hertz sinusoidal current and chops the hell out of it, right? So over here, it looks terrible. And because it looks bad here, it's reflected in the current we're pulling from the wall or from the AC power source into the transformer. So without it, it would be nice sinusoidal. But because of these diodes, it's not. It's full of noise, okay? So we're going to look at the waveforms here, we're going to look at the waveforms here, and then we're going to look at the waveforms on the output. Once we turn it into DC, it gets quiet again. It's beautiful. It's nice. Let's do it. I'm going to bring you over here. We're going to do this thing. All right, guys. So here is the setup. The main big old toroid transformer. That's a beast. And we're going into the rectifiers, bridge rectifiers. So primary input power is right here. The power is coming from this IT Tech programmable AC power source, 7321, IT 7321. Okay, so I'll show you that power in a moment. Oh, and then, you know what, the load, let me just show you that. The load's up here. I'm going to crank up the power and then I'll show you that. First, we're going to look at the input to the transformer, right? No EMI filter, we're just going straight in. And then we come around and then we're going to look at this stage, what's going into the bridge rectifiers, okay? And then we're going to come over here and look at the output stage. So we're going to look at those three stages. And I got my blast shield right here. I'll be putting that in front of this just in case. So I'll be looking at the Uni-T UP0 1204. So I'll be using this oscilloscope, and I'll show you those screenshots. Okay, and what we're going to be doing is we're going to be using this DP10007. Okay, it's going to be on times 100 mode, and that's going as differential voltage probe into the scope. Okay, and then we're also going to be using this McSig, another McSig part, this current probe, and that's the CP2100B, and it's going to be in times 10. And it's coming up here and coming up to channel 3, okay? So we're going to have our differential probe. We're not using this one. I'll disconnect it just so it's not confusing us. But we're using these two channels for looking at current and voltage, okay? So that's that. Now, the other thing we're going to be using is we're going to be using a CP503 McSig, this new differential probe, current probe, sorry. Super nice probe. And that is this guy right up here. And that'll be going to McSig. And I'll be showing you mostly the McSig screenshots, but I'll show you also the Uni-T in comparison, okay? And then the other thing is the differential probes back here. Okay, well, just knocked that one off. But the differential probes are going to come up here to channel 1. And that is the DP750-100, okay? Another really nice differential probe. So we're going to be looking at current voltage in here and the same current voltage in here, just as a comparison, just so you can see the Uni-T and the McSig together. McSig costs a little bit more, so we're going to see how the Uni-T stacks up. All right, there we go. Now let me go ahead and crank up the voltage. Sorry, it kind of bounces around on the screen. There's 40 volts, 50, 60, 70, 80, 90. We have to stop there. Right now we're at 80 watts. And if you notice, the wattage has really jumped up because it's charging those caps. We're at 1.6 amps right now. And up here on the IT8512A, the electronic load, I'm limited to 150 volts. So right now it's 135.88. And that's why I found 90 volts works well. We're at half an amp right here. We're going to creep that up. 6. Okay, now we're at 95 watts down below. 111 watts down below. Okay, we're at 0.8. We're 127, 0.9, 143. We're going to go to 1 amp. Okay, so, all right, so there we go. So right down here, we're at 159 watts and it's 0.64 power factor. So, all right, there we go. Okay, let's go look at the scopes and let's do this. All right, guys, so this is the waveform. I have 133.6 volts on the load. That's across both outputs. You know, they're in series. The input's 90 volts. All right, guys, turn on the measurements. You can see I have 90 volts coming in, RMS. Nice clean sine wave, it looks like, right? The current is pulsating on and off, like, you know, like a low frequency switcher would. It's going up as high as 8 amps, and RMS is like 2.8 amps. So 2.8. So it's going up more than 3 times the RMS. So peak currents are pretty high. All right, I'm going to show you a screenshot of what the Uni-T looks like and the measurements it has. It looks like roughly the same measurements. At the bottom of the screen, you can see that. It looks pretty good, right? All right, so now let's go look at the spectrum for this, okay? All right, there's the settings for the spectrum, channel 1. Blackman, normal, okay? So now let's go ahead and move that waveform over. Well, let's at the bottom of the screen, we can see it's going to be going to 6K. I want to go to about 1.2K so we can see the resolution. Now I'm going to move this over, and actually that peak is way off the screen because we're at 10 dBs per decade. Okay, there's 20 dBs, so that's on the screen now. Yeah, move that over there to the left. Okay, so we're going out to about 3 kilohertz to the right side of the screen. Okay, I'm going to bring the signal down right there. So that's 0 dBs, right where you see the M on the left side of the screen. Okay, 60 hertz is going up to 36.5 dBs. You can see the numbers there. And then the harmonics are pretty low. They're down below 0. They're down around 10 dB. And then you see them kind of drop off to 20, about the middle of the screen, and then drop off, okay? So that's the voltage, all right? So the sine wave looks pretty clean, right? So we're going to say 36 down to around -10 maybe, or -5. So we got at least 40 something dBs between the peak and the first harmonics. So that's looking pretty decent, right? Okay, so now let's bring out the math and let's change it to channel 3, the current. All right, guys, so now let's bring down channel 2, the current, okay? So there's channel 2, and that's the spikes. Now notice, there is no large fundamental at 60 hertz. I mean, we would like that because we like to have our power transferring at 60 hertz. The line frequency, the sine wave, that our voltages, but it's not. I mean, you can see it's down around 0, and the first 3 or 4 harmonics are pretty close to the same value. So what that's telling us, and then it rolls off like 20 dB or something, rolls off 20 dB for another 5 cycles, then drops off again a little bit. But what that's showing us is the current is all noise. It's very noisy. That peak current pulse, the first 3 or 4 harmonics are pretty much, maybe 5 harmonics, are pretty much making up the content of that amplitude. So yeah, it's not like the voltage where most of the voltage is the fundamental, and then we have some harmonics. This is like pretty much, the 60 hertz amplitude is equal to the second and third harmonic, and the fourth drops off a little bit, the fifth is a little bit more, sixth a little bit more, and then by then it's dropped off about 20 dBs, about the seventh or eighth harmonic. So that's very dirty power, okay? So that's what it looks like at the input to the transformer. All right, just different setup. I've moved the probes from the input to the transformer to the output of the transformer going into the board. So we have both positives on the top rail, and then the center tap in the middle where each winding, the bottom of the top winding is connected, the top of the bottom winding is connected, and then the bottom winding is over here, and we have the black ones on that. So we're looking across the 2 windings, okay, from top to bottom. We're going to do that on the output too, because that's where the load's taken. I didn't show you that before, but the load is taken from top to bottom. We're leaving the center, the return or ground, whatever you want to call it, it's left alone. We're looking from plus to minus. And we're going to do that across here too, just so the scale of the noise or voltages will be comparable to both input and output. Okay, so let's go ahead and do it. And I'm going to take the power levels and the currents the same as I did last time. All right, guys, so now what you're looking at is the output of the transformer. It doesn't look a whole lot different, right? Now we're putting 90 volts RMS in, but this time we're seeing 99 volts out. So it's a little bit more than a 1-to-1 turns ratio. The high voltage is 134 for the peak, but look at the peak, it looks so flattened off, right? Why is it flattened off? Well, because that peak current, it's a little bit less than what was in the input because the voltage is a little bit higher. So, but it's flatter. The voltage is flatter because you can see where the current spikes up, it flattens off the voltage because there's an IR drop. IR means current resistance, which is Ohm's law, right? Current times resistance is voltage. So we lose voltage across the winding of the transformer, which flattens off the voltage at the peak when the current pulses on. So now we're getting a little bit more distortion on the voltage, okay? And yeah, there we go. So I'm going to show you the Uni-T so you can see what that looks like. Let's look at the FFT again, okay? And let me pull it out. Let's start off at channel 1. And again, the voltage, channel 1, you see the spike up around, it's around 37 dB. The voltage a little bit higher, but the problem is the harmonics, they're right around 0 dB. The second harmonic, 120 drops down a little bit, but then the other ones are right around 0 for a couple. Maybe their third harmonic's around 0, and then it kind of starts to slowly drop off to about -20s, about the second pulse, right? I mean, where the yellow one is. So the noise has risen because the voltage, you can see it's clipping. So we have more noise now. As we go through the power supply, man, it's getting worse. And it's all because of those pulsating currents, that low frequency switcher, those diodes commutating on and off, turning on and off, just like the high frequency switcher where FET does it. Now there's no control on the diodes, they just self-controlled, but still they're switching. So as they switch, they cause more distortion on the voltage. Okay, now let's look at the current. All right, same thing. Current still terrible, right? Just like before. I mean, it's a big old pulsating current. That is not 60 hertz. I mean, it's at 60 hertz, the main cycle, but it's because of the straight edges and the flat edges at the bottom in between pulses. It's more of a, trapezoidal or square wave versus a sinusoidal wave, right? So yeah, the first 1, 2, 3, 4 pulses are almost equal. Let's see if I can turn off the yellow waveform so you can see it. I'll turn off channel 1, channel 2. So now you can see it a little bit more clearly, right? So the first few pulses, 1, 2, 3, 4, the fourth one rolls off, fifth one's a little bit lower, and it just kind of, the sixth one drops off a little bit more, and then it drops off a little bit, a bit more, and then, they kind of just slowly level off. That's just a lot of noise. That's a noisy waveform, okay? That's what that shows. All right, let's move on. Let's go look at the output and see what that looks like. All right, guys, so finally we're at the output. So now I've got both differential probes. They're both red ones here, both black ones there. So we're looking across, both outputs. So we have two outputs plus minus, but we're looking at, just like we did here, we went across the extreme outputs. Here we're going across the extreme. So we're leaving the center tap alone, the ground over here alone, okay? So that way we can scale them the same way, right? So same probes, and then I got the current probes over here going to the wires to the load that go up to there, right? Okay, so same load. I'm going to set up the loads the same way. So let's go ahead and let's look at the screens. Let's do it. Okay, guys, so now what we're doing is we're looking at the output, and we have 25 volts per division, and you can see the marker down here. I got the current and the voltage marker right on top of each other. Here I touched, yeah, you can see the voltage marker there, the current marker there, and the waveforms again look very even. Now the measurements down below, RMS for voltage is 132.5, high is 133.5. So again, looks like about 1 volt ripple maybe. And then the current, RMS and high are almost the same. High is a little bit higher, but you can tell the ripple current's going to be very low, okay? Now here's what we want to do. What we want to do is bring this out and AC couple the voltage, okay? And then what we'll do is we'll put it in the center of the screen, and then we'll zoom in on it. There's 2.5, 1 volt per division, half a volt per division. That's as close as I get. That's my best measurements, half a volt per division, okay? So if I freeze that for just a moment, you can see it's about plus minus half a volt. And it's, it's the typical, we charge the capacitors and then we discharge. Charge, discharge. So that's what we expect, right? And we put more volt capacitors, we can make that smaller, but the peak currents are going to get higher. So that's kind of a trade-off. So right now, that looks pretty good. Okay, so now let's look at the current. Let's get it running again. And let's do the same with the current. AC couple. We'll stick it in the middle of the screen. And then we'll zoom in on it. And wow. Okay, I'm going to turn off the voltage just so we can see this. I mean, look at that. Here, let me stop it. I mean, that is like 4 millivolts, 4 milliamps per division. So that's ridiculously small. And yeah, that's so small. Okay, let's go look at the FFT again, okay? I went and changed the time per division 10 milliseconds. It was at 5, went to 10, get a few more cycles. It's not going to make a big difference, but let's see what we see. Okay, there's the math. Pull it out. We're going to look at channel 1 to start with. All right. Now look at that, guys. Here, let me turn off that current waveform too. All right, there's a nice clean. That's the voltage we're looking at. And look at that. It's that first peak is measuring at minus 17.7. You can see that in the top left. Now, that's almost on the grid line of minus 20, right? And then the second one's below that, third one, it just gradually drops off. So there's no significant harmonic here because it's just, they are harmonics of the 60 hertz, that ripple we saw, which we expect. So this is what we expect. And, you know, it's, God, it's way down here at minus 20. So that is great. Now let's look at the current. Let's go back and look at that. Let's go look at channel 2 and see what that one is. I think I changed the screen accidentally. Oh, I went to 10 dB. Okay, there we go, 20 dB per channel. Okay, now look at the current. It's way below minus 40. It's like minus 66. So, man, look how, I mean, that is super clean. That is fantastic. All right, so there you go. Now, I've done separate videos showing you this stuff. Today, I just tried to do real quick video to put it all in one video so you can go boom, boom, boom. And you can see how from the current looks terrible over here. So who cares if there's this little minute stuff, this RF energy and all that stuff that doesn't mean anything, because the current over here is terrorized. It's put through these big churning diodes. And then over here, it's beautiful again. Voila. Thank you, bulk capacitors. That's without even, I mean, there's teeny little polycaps. That's before we ever do any real filtering, guys. This is just taking the power and converting it and processing it. This is hard processing. We don't have any filtering here. We don't really have any filtering here on the bridge diodes. Let me see. Yeah, I don't see any caps down there. We'll put some caps down there on the real stuff. And so there's filtering along the way. This is hardcore power. So worst case scenario. And you can see how it comes off the wall. Well, if we just put a load on it without the diodes, it would have looked nice and sinusoidal. Okay? But then we beat the crap out of it over here. We turn it into something else because it's going to be DC. And DC is beautiful. It's nice and clean. Yeah, the voltage has ripple. So over here, the voltage looked much better, right? Because it's sinusoidal. But then over here, and on this side, had flat tops. So it's starting to look worse. Our diodes are ruining things. They're beating up our clean power. And then people are worried about these minute changes and stuff. And it's ridiculous. It's absurd. I could just say, go all day long and talk about how crazy it is. Super expensive scopes. The scopes I have here, all the equipment I have here, cheap power cables. Why? They don't matter. All right, so beat that dead horse. So anyway, for you guys that haven't fell into the believers camp yet, I just want to make that point. But I'm also showing you what power looks like in a low frequency switching, low frequency power supply. Okay, now we're going to move on to the PFC and to other switching power converters because I have a thing for JAT that I got to do. So away we go. Thanks for watching. 2 thumbs up to my patrons as always. 2 big thumbs up to Danny, my team member, and the rest of my members on YouTube. Thank you guys. I think I have 9. That's awesome. That's amazing. I love that. Oh, and 2 big thumbs up to you guys that have bought me some coffee. And I'm going to, God, I kind of did, man, maybe I should drink a beer after this rant. Let me know what you guys think of the video. Was that helpful to see how the powertrain worked? I hope so. All right, guys, thanks for watching. We'll see you next time.